All right, hello again. This time, the video is going to be about exponential functions like before, except we're going to be looking at some transformations also. The equation that I have written here at the moment, y equals a times e to the power of x minus b plus c. This is just another exponential function like we've looked at before. However, there are a few different elements that exist in this equation, such as we have an a over here, we have a minus b up here, and we've got a c here. What these letters stand for are different things that we can do to the equation, different ways that we can alter the equation. In particular, these are called transformations. So we can multiply the whole function or multiply the base number and whatever is attached to the base. We can multiply that by a, and a can be some particular number. We can add or subtract values to the variable, which is the power up in the power. And we can add and subtract numbers to the rest of the equation down here. And this has different effects on what the graph should be, what the graph should look like. This is a table. I'll zoom out. This is a table where it describes exactly what will change in the graph. So in particular, there are a few words we have to identify here. The three types of transformations that you can have are dilations. So that's one, dilation. We can have a reflection. We can have something called a translation. And they're the only three things that we can have. But they can look different depending on the precise way that we do it. So for example, the graph I've got next to here is just your typical exponential function, e to the power of x. If I multiply by some number, the whole function, this is going to be a dilation. If this number is, say, greater than 1, so if I go 2 times e to the power of x minus 1, this graph is going to end up being shifted towards the y-axis. It's going to end up being steeper and taller. Okay. If I multiply by a number between 0 and 1, say like a fraction, if I make this half e to the power of x minus plus something, then that means it's going to make it a bit, might come out like this. It's going to be a bit shallower and it's going to be towards the x-axis. So that's a dilation. A reflection occurs when if a is going to be a negative number. So if this a here became a negative number, the graph is going to flip upside down. So the whole graph would look exactly the same, but it will just be a mirror image across the x-axis. So flips upside down here. If, I'll go to the next one. If we're talking about a translation, we can do a translation left or right, or the graph can move up or down. The parts of the transformation equation that affect this are letters B and C. So the graph can move depending on what B is. The graph can shift to the right or shift to the left. So if it's shifted to the right some amount, it might look exactly the same, except just shifted. So it's still going to be the same steepness, but it will just be moved over. And the same if we move it to the other side. A vertical translation comes from letter C here, and vertical translation just means up or down. So if we add or subtract a number, it means the graph can move down, for example. So let's say if we go -5, if C was -5, this graph would look exactly the same as that. And I'm just sketching it here, but It would have the same steepness, it would have the same proportions, but it would just be down. And likewise for going up, if it was +5, it would just be pushed up 5 units. The reflection in the y-axis, so this last one over here, occurs if we put a negative in front of the power. And a reflection in the y-axis is just a mirror image reflection across the y-axis like that. So instead of flipping it upside down, we are flipping it across the other axis. So it would just look something like that. It's not a very good drawing, but I hope you get the idea that it's a mirror image across the y-axis. So the purpose just for this video now is to just sketch some exponential functions that have had some transformations in them. That's all. There are a few other things we want to look at, such as domain and range and how to state the transformations. And I'm also going to talk about how we can read the asymptote from the transformation too. But we'll go to this first problem. And if you think you can do it straight away, pause and try it, and then compare it with what I've done here. Anyway, to sketch this, I still want to try and start with the x and the y-intercepts if they exist. Like, that's something we should always consider. So let's go to, say, let's make x equals 0 and solve for y. So I'll go y equals 2 to the power of 0 plus 3 minus 5. So we've got 2, this becomes 2 to the power of 3 minus 5. And 2 to the power of 3 is 8. 8 minus 5 is 3. So that means our y-intercept is x0, y3, just like that. So let's just go ahead and put that on. So the y-intercept, let's just make it here, 3. So we know the graph will go through this point. Let's see what happens if I want to find an x-intercept. For an x-intercept, we want to let y equal 0 this time. So I'll go y is equal to 0, and it was 2 to the power of x plus 3 minus 5. So we'll take the 5 to the other side, becomes plus 5, 2 to the power of x plus 3. And I hope that we can see now that we're trying to solve for this x, which is in the power. We need to rearrange using logarithms to get that x out. The base number is 2. So log to the base of 2 of 5 is equal to x plus 3, which is the power. The log is always equal to the power. And if we just get the x by itself, it leaves us with log to the base 2 of 5 minus 3. And if you solve that one, it comes out to, we'll write it here. If I round it to 2 decimal places, it's negative 0.68. So that means the x coordinate is negative 0.68. We'll just round it to 2 decimal places and 0. So let's find roughly where that should be on the graph here. If we say this is negative 1, then let's say here is negative 0.68, roughly. I'm just sketching. So this should provide us with the overall appearance of what the graph looks like. The thing with transformations now is that before we would know precisely what the graph should look like, if we were just sketching a basic exponential function with no transformations. However, the graphs can move around now on the plane, and we need to consider a few other things. In particular, we should consider, first of all, where the asymptote is for this graph to give us a better bearing of where to sketch these, well, how to connect these points. The asymptote is, well, for an exponential function, the asymptote is always horizontal. It's always flat. And we can find it very easily by looking at how the graph has moved up or down. In this case, the graph has moved down by 5 units. Normally, the asymptote is when y equals 0. But if we shift the graph down 5 units, the asymptote will be at -5. So that's what I'm going to do here. I'm going to say this is -5. That's where the asymptote is. So everything in this graph should exist above -5. And we know that because we've got the 2 intercepts there that we've verified. So now I need to connect these 2 coordinates, considering where the asymptote is and knowing what the shape of an exponential graph looks like. So what we end up with this situation, I'll try my best to sketch it properly, is that the graph takes on this appearance. Once we've got the graph, we need to look at it and state what we think the domain and the range is. So the domain, remember, is all of the x values that this function exists for. When you look at the graph, I think it's straightforward to tell. The x values go all the way to -infinity, and they go all the way to +infinity, because the graph continues to rise. It continues to rise, but it also still moves in the x direction as well, and it will do that forever. So the domain is going to be all real numbers. The range are all the possible y values that exist for this function. So if we look at where the smallest y value could possibly be, that is -5. And then how far up does the graph go? It continues to go. It will go all the way to infinity, which is what we can consider. So I'm going to write -5 is the smallest possible y value, even though it never touches -5, but that's our barrier, and all the way up to +infinity. To indicate that it never touches -5, we are going to use a curved bracket. And that tells us that it comes all the way to, -4.9999999, right up to that -5 without ever touching it. So we use a round bracket to signify that. One final thing is we should state the transformations as well. So how is this graph changed? If I go back to the original function here, the transformations are, of course, the -5 and the +3. This 2 is not a transformation. This 2 is the base number. That's built into the function already. So there's +3 and -5. The -5, we can say that the function has moved down by 5 units. The 3, we can say it has moved to the left by 3 units. One confusing factor here is it is +3, I know, but we have to change the sign. So it's not it's not going to the right, it's going to the left. We just have to change the sign, so it's 3 units to the left if it's a plus. And there we go. I have one more problem here. and there are a few more transformations involved. So we'll just take them one by one. But we want to follow the same steps with this one. And again, pause the video if you think you can solve this one and then compare it with what I did. Let's start with finding the y-intercept again. This means I will let x equal 0. So -2 e to the power of 0 plus 3 minus 1. And of course, we can just type that into our calculator to check, or you can try and figure it out yourself, but it comes to, I'm going to round it to to the nearest whole number, but it comes to -41. It's actually -41.17, but we'll round it to -41 for simplicity's sake. So that means our y-intercept is 0, -41. Let's consider any x-intercepts here. So I'm going to let y equal 0, -2 e x plus 3 minus 1. So we'll take the 1 to the other side. It becomes +1, -2 e to the x plus 3. And let's divide through by -2. So that's going to give me -½ over here, e to the x plus 3. And we'll keep going. E is the base number, so I'll write it as log to the base e of -½ is equal to x plus 3. Already there's a problem. We can stop here and say that, okay, we're taking log of a negative number. There's not going to be a solution to this. So no solution. And I'm sorry, that was not helpful to try and find the x-intercept. What we can consider next is perhaps, let's look at, I'll put in the y-intercept first. I forgot to do that. So let's say -41 is going to be down here. So we know it's going to go through that point. But without some other reference, whether it's another coordinate or, you know, looking at the asymptote, for example, we don't really know where this graph, how to connect this with the rest of the function. But because we hopefully understand the way that the graph has moved, this graph has moved down 1 unit. That means instead of the asymptote being at y equals 0, the asymptote will be at y equals -1. So let's put that in at least. And I know my graph is not to scale, but yeah, we can still sketch it. So at this point, we could have a graph that goes in this direction, intersecting with there, or it could come in this direction, intersecting with there. It should still have that exponential curve look to it. So what we can think about doing now is realizing that we also have a negative in front of the whole function. This is a reflection. If we start with a basic exponential function, and I'll just sketch your standard one here, it would look something like that. This negative in front of the whole function tells us that it is flipped in the x, across the x-axis. So I think this is enough information to tell us what this graph really looks like. So if we reflect it across the x-axis, it's going to come across like this, and it's going to intersect with -41. And that is just enough to sketch this graph. That is just enough to sketch this graph. we can find another coordinate if we wish. But if you do that, and I had already calculated it for, say, x is equal to 2, and if x is equal to 2 in this function, try it yourself, you end up with a y value of negative 297 something. So this is a really, really, really steep graph, and negative 297 is way off the scale of what I've got here. So you can check that and know that the other coordinate is further negative. So we know that it must connect in that direction, and it must go more wide as x increases. It's just very, very steep. But you can see that if you know how the graph has moved around, when you look at the asymptote, then you can find other ways to imagine what it should look like. So we now just need to consider the domain and the range and what transformations we've observed. So the domain is all of the x values that the function exists for, and in this case, it is still all of the real numbers. The range, remember, is all of the y values that exist for this function. Looking at the graph, the smallest y value is going to be negative infinity. Negative infinity. And that comes all the way up to negative 1 without touching negative 1. Like that. Negative infinity to negative 1. Let's discuss the transformations now. The transformations in this function, I'll circle them, I'll underline them. Negative 2, the negative and the 2 are two different transformations. The plus 3 and the negative 1. So the transformations here, there is a reflection. There is a reflection in x-axis. Reflection in the x-axis. That was this thing here. There is also, we are multiplying the base number by another number, 2. This was called a dilation. This was called a dilation, and it's a dilation. The number is greater than 1, so it's making it steeper. It's making it taller. When you make it taller, it moves closer to the y-axis. So it's a dilation towards y-axis. And we've got a plus 3. We saw this one before, in fact. This is left 3 units. And we've got the shift down. And the shift down is, down 1, down 1 unit. There's quite a few transformations there, but I think if you understand both of these problems and you solve it in the ways that I've done it, you can solve any, and you can sketch any of the graphs because all of these questions are very similar. They're just involving different transformations, but if you know what to expect the shape should be, if you understand how the graph moves, if you follow the routine of finding the x and the y-intercepts first, you can quite hopefully easily sketch this graph of any of them. So I'll zoom out a little bit there. Anyway, I hope this has been useful, and yeah, please try some of these problems yourself, and yeah, see you later.